Welcome back. In this episode, we're going to create our parser. Recall that this will take the list of tokens created by our lexer and generate an AST, or abstract syntax tree. So, let's get into it. What I want to do first is just add one simple line here. I want to add a condition that if our line is empty, so the user didn't enter anything except the enter key, then we should just continue and ignore anything. So now if we run this, we can just type enter repeatedly and nothing happens. But when we enter tokens, we get our tokens. This just gives more freedom to our users. Now let's create a parsing module. And inside of it, let's create a parser.py. First, we have to import our error from util. Now we can create a parser error class, very similar to what we did with our lexer. Now we can make our actual parser class. Let's give it a constructor. It needs a reference to the tokens that we're working on, and it needs an index inside of that list. Let's give it a next method, which will simply return the token that is in our list at our position. Now, let's give it a take method. We can take the next token, we can increment our index, and we can return the token. Next, let's start work on our makeTree method, which will take in the list of tokens, and we'll have to set our internal variables to the tokens we pass in, and we set the index to 0. In a moment, we'll come in here and construct a node. Then after, we want to check that if the next has end of file, we can return the node that we constructed. Now, we haven't implemented has for our tokens, so let's do that really quick. We can come into our token class and add two convenient helper methods. One is has, which will take a list of strings and simply will return whether or not our string is in this list of strings. Similarly, let's create an of with a list of kinds, and we will return true if self.kind is in the list of kinds. So our parser will expect an end-of-file token, and if we don't have one, we should raise a parser error. We can pass it the next token, and we can say that there was an unexpected token. And we can print out that next token. Now, we can add two more helper methods to our parser. One where we say that we are expecting that a token has some strings, something in some of these strings, and all this does is if the next token has these strings, meaning at least one of them, then we can simply take that token. Otherwise, we throw an error. We give it the next token and say, expecting has something inside of these strings. Once again, we can make an expecting of with a list of kinds, and then we can call of on the next token. If it is true that our next token is of one of these kinds, we take it. Otherwise, we raise an error. And I will simply copy paste previous error and change has to of and change strings to kinds. Now, we need some class to represent our nodes. So in parsing, let's create a node.py And we will have to import some abstract class functionality from ABC. We want to import abstract base class and abstract method decorator. We can create our node class as an abstract class, and we don't know precisely what information every single node is going to have, but we know that we want some sort of representation for them. So let's create an abstract method, and let's call it nodes. And since it's abstract, we don't give an actual definition for this function. We just say pass. But later, when we create nodes, we can implement this, and we can use this value to get all the components stored in the node. So we can use this to create a wrapper, for example. And importantly, we'll want a recursive way to print out our tree so that we can actually analyze it. Let's create a tree wrapper. And as part of the recursion, we need a prefix, which will be defaulted to a tab, which I will say is 4 spaces. The string should start as the name of our node. And we can get the nodes from self.nodes. Now, if we iterate over those nodes using enumerate to get both the node and the index, if we create a variable to check if we are at the end of our list, we can set certain symbols that will look nice. And these are very specific characters, and you'll want to copy them from the description. So our symbol can be these if we're at the end, otherwise these symbols. And you'll see in a moment why exactly we are using these. We need a prefix symbol, which will be nothing if we're at the end, otherwise this symbol. Now we need to call tree wrapper on every single node to get its own representation, and let's store that in a variable called node string, where we call tree wrapper on our node, and we have to give it a new prefix so that it's formatted correctly. We start with our prefix, then we add the prefix symbol, and then we add 4 spaces. Lastly, we can add to our string a new line, followed by our prefix, followed by our symbol, a space, and the node string. And we can exit the loop and return the string. Now if we come back into our wrapper, we can simply return self.treeWrapper. We need to implement a mark method. So for node and self.nodes, we can call node.mark. And if our node is another node, this will be called recursively until one of our nodes is actually a token, in which case we call the token.mark. If we want our errors to work correctly, we also need to come up to the top and add a property to our nodes and call it line. Simply return self.nodes at 0.line. Because we're guaranteed to have a nodes method, and every node will have at least one thing in it. If that thing is a token at the beginning, then we'll simply get the actual line, and if it's a node, it will just recursively call this property until there is a token at the beginning. Lastly, if we come down here, we need a class method, which is abstract. The order of these decorators matters, and we can call this method construct, and we can give it a parser object to use to construct the node. This will allow us to create node files which know how to construct themselves using the parser that we've created, and this simplifies down parsing immensely. In this node file, we'll also create 2 more helper classes. One class will be primary node, which will represent nodes that only have 1 token, So we can give it a constructor. And like I said, this constructor takes a single token, and we can simply store that token. We can implement our nodes, return a list containing our token, and we can simplify our tree wrapper for nodes that only have one token. How about we just return, we want our name, then once again we need to copy some symbols, and we can just print out our token on one line. Now this reminds me, because our nodes might be tokens, we also have to go back into the token class and implement tree wrapper for tokens. We don't care about the prefix, so we can just use underscore to ignore it, and we will simply return the wrapper of our token. We need one more class in here, one to represent binary operations. We can call this binary node. And before, I said that these classes are both nodes, but they're also abstract classes. That wasn't clear. Now, binary nodes will have three components to them. They will have something on the left, an operator, and something on the right. So we can just come down here and store these. Next, we can implement our nodes method. Left, op, and right. Now we want a construct method, but we want to actually make more of a tool for nodes that implement binary node to call in their own construct. So instead of defining a construct, let's create a new class method and call it construct binary. And this will take the class, the parser, but it will also take the actual class that is calling it, the class it wants to make, and a list of ops. Now this will make more sense when we actually implement one such class, but for now let's just continue with this. So we can make a node which will be part.construct, we'll pass in the parser. So this part is a node class, and then while parser.next has any of these operators, we can then recursively construct the node. We can take the op, and then right is equal to, once again, part.construct, we give it the parser, and our node is then make, which is a constructor, and it needs three things: the left, the op, and the right. And at the end, we will return the node. Now we have everything we need to start building our expressions from our grammar. Inside of parsing, let's create a new package and call it expressions, just for organization. And let's start by creating expression.py. Now this will be an abstract class, so we'll have to import abstract base class from ABC. And we need to import our node as well. Let's construct a class, expression. This is a node, but it's also abstract. This way we don't have to implement those abstract methods. And let's just implement the class method construct. And for now we'll do nothing. But what we have to do is work our way up in the grammar. Let's now, in our expressions, construct a new expression, an additive expression. We need to import our node. In this case, an additive expression is a binary node. And you see, we have an error here because we're not implementing all abstract methods. Since it's a binary node, we have our nodes implemented, but one thing we need is to implement construct, which for now will do nothing. Now, we don't know what we have to construct yet because of our grammar. Our grammar requires multiplicative expressions, which we haven't implemented yet. But now that we have an additive expression class, we can go back to our expression and import it. And now our expression construct can simply return additive expression construct, passing in our parser along the way. And now our expression class is done. Remember, our expression doesn't actually do anything, it's just like an alias for our additive expression. Next, we can make our multiplicative expression. Again, we need to import our node, which in this case is a binary node again, and we can make our class. And now the process of making these nodes it will very quickly become familiar. It is, to an extent, boilerplate, but I do think overall it's worth creating. Now, we can go back into our additive expression and import that node. Now you can actually see how the construct binary is going to work. So what we can do is we can return class.constructBinary. We give it a parser. The make is our current class. So you remember before we had make with the 3 components. That will essentially be replaced with additive expression with the 3 components, which is the constructor that we want. So the class. And then we have the part, which in this case is the multiplicative expression class. And then we have to give all the operators, which in our case are just plus and minus. And now our additive expression is done. All of the logic, for the most part, is inside of our binary node, and we can reference it using this very simple method. Now we can close this out and similarly create a new expression. Exponential expression. We need to import the node again. Again, we're going to need unary expressions to complete this construct, so first let's just finish up multiplicative expressions. This will work like before, except we have 3 operators in our list, so return construct.binary, we give it the parser, we give it our class, we give it exponential expression, which we have to import first. And we give it the list of our operators. Multiply, divide, mod. And now our multiplicative expression is done. Once again, new file, unary expression. Some of these constructors are really simple, some of them aren't. But more importantly, we'll be able to add our interpreter into these files simply by creating an interpret method, which each node can just implement, and it will make things a lot simpler. So now we need to import our node. In this case, our unary expression is a different kind of node, so we'll have to do some things manually. Now we have to implement a constructor for this, and a unary expression is an operator on the left, followed by some other expression, and we can simply store these. Now we can implement our nodes, return our operator, and our expression. Now keep in mind, you have some choices here for which tokens to store and which to not. Anything that's in nodes will end up being printed out, so you get to choose which tokens are important, so long as there's at least one thing in your nodes. Now we can come down here and make our construct. And we need primary expressions, our last piece of grammar, before we can implement this. But now we can go back into our exponential expression. While this is a binary node, our binary construct only works for operators that go left to right. So we have to manually construct our own constructor here for exponential expressions. First, from unary expression, we import our unary expression. We then start by constructing one. And then if parser.next.has the operator, if that's not the case, if there is no exponential operator, we simply return the node. Otherwise, we know that there's an operator, so we take it. And then we try to construct another exponential expression, which will either return a recursive construction of exponential expressions or just the unary expression if there are no more operators. Then we can actually construct this node. It is a binary node, so it has a left an operator and a right, and that's our exponential expressions constructed. So we can close this out. We now make one last file here for our primary expressions. Node and primary node. Let's make a primary expression class. And now this is going to represent all of our bracket expressions. Things like parentheses, our floor and ceil brackets, etc. Let's give it a constructor, and it will have a left bracket, an expression, and a right bracket. We also then need a nodes. And we need a construct. Now, there's only one last thing we need here. We need a number class, which is separate. And this is a primary node. This needs a constructor. And we simply return a new number with parser.expectingHas or expecting of type number. And now we can actually begin properly constructing everything from the ground up. So if it's not the case that the next symbol is one of our brackets, so an open parentheses, an open absolute value, floor, or ceil, we simply return number.construct, where it is expecting a number, and if there isn't a number, then we get an error, and that can be useful. Otherwise, we have our left. We can then make an expression. Now, there's one important part here when we construct our expression. We can't just import expression here, because then all of our nodes would have a circular import. So what we need now is in our parser, we can import our expression from expressions. And we're going to use this down here to make our tree in a moment. But until then, let's just create a simple property called expression, which is simply a reference to the class. Now, we can make expressions anywhere if we reference it through our parser. And to get the right bracket, we just have to be a little careful because these three brackets are the same for their closing, but parentheses are not. So we are expecting it has one of these. If it should have a closing parentheses if the left symbol is an open parentheses, otherwise it should just be the string of the left bracket. And then we can return a new primary expression with left, expression, and right, just as we expect. Now, I believe we just have to finish our unary expressions. Come in here. First, we have to import our primary expression. Now we can come in here and say parser.next has one of these operators. We take it. We construct a unary expression so that it works recursively. And then we construct the node and return it. Otherwise, we just return a primary expression. Now, we just have to link a few things first, and then we can test. We have to come into our parser, go down to make tree, and we can actually now construct the tree. Node is expression.construct, and it needs a parser, which will be self. And then, if we get to the end of our list, we can simply return the node. Now, if we go into main, we need to import. We can construct a parser object. And now down here, we probably still want to print our tokens, but now we can say tree is equal to parser.makeTree and pass in the tokens. Then when we're done, we can print our tokens and we can now print our tree. So let's see where we are. That's a very simple error. If we come into our parser, we need to make this a local import. And I will then put it below since it's local. So if we try again. In our exponential expression, we have to do a similar thing. Make that a local import. And now, if we say 5 plus 6, we get our list and we get an additive expression with 5 plus 6. Let's try minus minus 10. Unrecognized symbol. So let's look into our lexer and see what caused this. It seems we have an equals here when we should have a minus symbol. So now if we try this again, you see we have our correctly nested node. Let's try the problem from the overview episode. We have the division last, then we have the multiplication before. We then have to do the parentheses. We have to add, and the first thing we do is negate, which is exactly what we have. So our parser is working. In the next video, we can begin work on our interpreter.